Hi everyone, welcome back to the Chem 14B lecture series, and we are now at part 3 of our class. And what we're going to learn from this class is how to represent organic molecules and how to draw them and so on. The one to remember is that one of the most important skills that I want you to learn is in this particular portion, and it's how to draw the skeletal structure. Now, the skeletal structure is basically a shorthand on how to represent this actual three-dimensional model of the atom itself. So, for obvious reason, it's kind of hard to draw these things, geometrically, and to draw a tetrahedral because it goes in and out of the board. And if people are not particularly very artistic, it's really hard to draw these things. Now, the skeletal structure is basically an improved version of the Lewis structure. You can see that the Lewis structure here is just all the carbon molecules seems to be linear from one another. But of course, individually, they're all tetrahedral. Right? So this is our tetrahedral. So what we want to have is a model that both describe how the bond is going on, as well as geometrical property. And the last one is that we want to be able to draw it very easily as well. And in order to do that, we essentially comes up to the skeletal structure, which looks like this. To draw the skeletal structure is actually fairly straightforward. There are several rules. The first one is you represent carbon molecule as kinks and edges. So for example, this is what I meant by kink, and this is what I meant by edge. And the next one is that we're going to eliminate hydrogen bonded to carbon. Now there's a reason why we're going to eliminate the hydrogen is that in organic reactions, the hydrogen is more or less is not very reactive. So we usually don't care too much about them. And if you ever try to draw a Lewis diagram, there's a bunch of hydrogen molecules attached to it, and this is actually going to be very time consuming to draw. So instead, in the skeletal structure, we're going to try to eliminate it. And we will try our best to maintain the geometrical model as well. So for example, this is the ball and stick model of the Lewis diagram that we have over here. And I'm going to eliminate all the hydrogens that are bonded to carbon. Okay, so these are all hydrogens, and I'm going to not draw them in the structure. And this last structure here is what we have. And as you can see, that the model now looks like that, which is what we have over here. So that's essentially the way to draw the skeletal model. As always, the best way to go about these things is just practice. Let's try to practice in drawing a large variety of skeletal model. Now we'll try with this one. This is an easy one. So this is a structure of, I think, acetic acid. So let's try to draw the skeletal model in this one. And remember, first we're going to eliminate all the hydrogens that are bonded to the carbon. So these three hydrogens are bonded to a carbon, so I'm going to eliminate them. But I'm going to keep this one because this particular hydrogen is bonded not to a carbon, but rather to an oxygen. So I'm going to keep that one. And then I'm just going to represent the carbon here as kinks and edges. So I have carbon number 1, carbon number 2, and then on number 2, we have a double bonded oxygen and then an OH group. Okay, so I have carbon number 1 is here, carbon number 2. So I'm just going to simply connect the dot between the two. So that's my 2 carbon. And on carbon number 2, I have one side is an OH bond and the other one is a double bonded oxygen. Let me actually make that a bit clearer. There. Now we're done with the skeletal structure of acetic acid. And more or less it looks like that. See, it's very, very easy and short to draw. That's why we're going to be using the skeletal structure, because once our molecule becomes more and more complicated, it's really, really annoying to keep having to draw the hydrogen. So let's do the second example, which is this one. This is capsaicin. This is a molecule that is responsible for the spiciness if you eat any chili and so on. So what I want you to try to do is just pause the video and try to draw the Lewis diagram of this molecule. Sorry, not the Lewis diagram, the skeletal structure. Remember, we're going to eliminate the hydrogen and we're going to represent the carbon with kinks and edges. The one that I want you to notice is that some of these carbon have double bond, like that one. And of course, there's nitrogen there, there's double bond there, there's nitrogen. So just make sure that you notice those things. And the next thing that I want you to do is also count the carbon. Count the carbon, because you want to make sure that the structure that you draw exactly have the same number of carbon molecule. Okay, all right, go ahead and pause. All right, now if you're done with the structure, let's try to see if you have the same thing. Now I'm just going to start from this end, just because this hexagon looking thing, or the aromatic group, is the most prominent one, so I'm going to start from there. So I know initially I have a hexagon that looks like that, and I have a double bond there, and on this particular carbon here I'm going to have an O and then a CH3 bonded to there, so there. On the next carbon here I have an OH group attached to it, so there, an OH. There. Now across from it I have another carbon molecule bonded to it. So now I'm on carbon number 1 here. I'm just going to call that number 1. And then next to number 1 I have a nitrogen. And remember, this is tetrahedral, so I have to kink it a bit. And then there's a hydrogen attached to the nitrogen. Next to this nitrogen I have a carbon with double bonded oxygen. And then the next one I have a CH2, CH2. Right, and then I'm going to go to the next one. I have another CH2, another CH2, and then I have a carbon molecule, but this carbon molecule have a double bond. So I'm just going to draw a double bond here to the next carbon, and the next carbon is bonded to another carbon molecule, and there's 2 carbon molecules sticking out of it. So I'm going to go one there and one that way. Okay, so now we are done with the skeletal structure of capsaicin. Okay. Let's see. Let's do one more example on doing the skeletal structure. And here, I want you to be able to draw including the triple bond. Now, there's a thing about triple bond is that all these 4 carbon molecules are all linear to one another. That is, if you put them together, the 4 carbon molecules there are going to line up to one another. So, right, because the bond angle here is 180, sorry, not 120, 180 degree. So now I want you to try to draw the skeletal structure of this as well. Again, try to pause, and when you're ready, replay it, and I'm going to draw the solution for you. And again, that's my hint, is that the triple bond, all 4 carbon molecules are 180 degrees from one another. So go ahead and pause. Okay, hopefully you've tried to draw the molecule on your own, and let's see whether we get the same result. So I'm just going to start from this end, just because that's where the triple bond, and I kind of make a comment about the triple bond. So I'm going to have carbon number 1. I'm just going to label my carbon 2, 3, 4, 5. So the one to notice is that this particular molecule is 5 carbon long. So I'm going to start with carbon number 1. So I have carbon number 1. It's bonded to number 2, and number 2 is bonded triple bond to number 3, and all the way to number 4. Again, this whole thing is 180 degree because they're all linear from one another. Okay, so that's number 4. And then it's going to be bonded to number 5, and this bond is a double bond. Now I'm done with all the carbon molecules. So this is 1, 2, 3, 4, and 5. And then let's kind of put in all the functional group. Now in carbon number 1, I have an OH group. And remember, this is a tetrahedral, so I have to put a little bit of a kink. So that's an OH group. And this one here, on number 5, I also have a Cl. So I'm going to draw it this way and put a Cl there. So this is the skeletal structure of the bond that we have on the top. This one is just kind of a bit, whenever you're drawing triple bond, it looks a bit weird, but I do want to emphasize that the triple bonds are all linear. Okay, so yeah, it's the most weird one to draw. Okay, now I'm going to do one last thing to mention for you. The rest is just really memorization. And then when we put in for the next video, I'll put in functional groups. Now, the one I want you to memorize for now is the name of these organic molecules, or carbon chain, or carbohydrate. Not really. They're really called alkanes. And essentially, if you only have one carbon chain long, so just one carbon, this is going to be called a methane. So one carbon is called a methane. If you have two carbon molecule, it's called an ethane. 3, propane. 4 is butane. So butane is one of those things that you put in your lighter. Pentane is 5, like pentagon. Hexane is easy as well, because it's hexagon, so hexane is 6. Heptane is 7. Octane is 8. Nonane is 9. And decane is 10. Now, I do want you to memorize this, because we're going to go into the organic nomenclature, and essentially I want you to be able to name a structure based on its structures and so on. And essentially the best way to go is trying to remember the name of all these 10. And this is actually one of the best preparation that you can have for 14C, because you're going to be doing something like this as well. Okay, so I'm going to end this particular video. This is part 1, and for the next part, I'm going to go into organic functional groups.